this thing on,
Huh? Okay. At least I have a tie this time to.
What?
At least I have a tie this time, actually.
Nice. I'm going to go ahead and hit start, so we'll be live streaming starting now.
Okay.
And then I'll edit the front half of it where it's all a bunch of
Us standing around.
behind you. All right, so I guess we'll get this started. This is a welcome everyone this morning for Matthew's PhD defense. Matthew, I managed to professor years ago. He was getting his master's degree with Dr. Igor Bolinoff, working on the fluid side of things, and joined the plasma group after he got his master's degree to pursue his PhD in plasmas. Since then, he's been working with open developing technologies for embedded ion energy analyzers for commercial etch reactors. So with that, I'm going to thank the committee, all of our guests, and we'll go ahead and get started.
Great. Thanks.
Oh, one quick question. Would you prefer questions during or after? Normally we split them up for a defense where the committee will ask questions separately. So probably the best thing to do for this one is we'll just hold questions to the end. Because unlike prelim exams that you may have cited before, these will be, they're separated into questions from the public, and then we kick you out, and then we have our questions too. So we'll just, we'll keep the questions to the end and let you blast through the presentation.
I think it's better that way since the presentation's kind of long anyways.
Okay.
So, thank you for that introduction, Dr. Shannon. As I said, my name is Matt Talley, and the work I've been doing Retarding field energy analyzers, which you can see one right up there, and I apologize if you can't see the red little dot, but it's there. And optimizing and designing them for high voltage operation in the electrode of an industrial coupled system. So here's a quick outline of what my talk is going to go over, and the main bullet points are introduction and motivation of why this work is important, but as well as going into the simulations I used in designing the RFEA, and then the actual process of installing it inside the electrode of an industrial system and then testing it in both single frequency, dual frequency, argon plasmas, as well as in plasmas that have a chemistry more consistent with what's actually used in process. So why do we need to understand or know about the energy of the ions in a silicon etching process? It can be quite important because, one, for example, we see an ion energy distribution function right here, a probability function. And it's plotted in a 3D plot based on the amount of low-frequency current that's being applied to bottom electrode, or the electrode that you're taking this ion energy measurement at. And this one was done through a plasma circuit model. And it shows you how, based on that that frequency and the percentage of that frequency used, it changes the shape of the IEDF. It changes the energy that the ions have. So we know that the ion energy changes based on that, but what does that actually do in our process? And so if you look at a silicon wafer and you're trying to etch a trench like that, you want the to be as straight as possible. You want the top to be the same size as the bottom. However, based on that 2% of low frequency power that you're applying, you can actually change the shape, how closely related the top is to the bottom, whether they're the same size or not. And again, that's the same idea. Because the ion energy is changing, the bottom portion of that trench is changing sizes, which is important to know for our actual manufacturing processes of the silicon wafers. Purpose on this work, since this wasn't my work that I did, but I would assume it's because of variability with the actual measurement size, the signal that's coming in, noise ratio. Yeah, two are quite large, and there's some variability. But even if with those large error bars, you still kind of see that increasing trend. So for another example, there's also been work showing that you can have an ion energy distribution function, or IEDF. And so typically in a dual frequency system, you have two frequencies. You have a frequency applied to your top electrode, a frequency applied to your bottom electrode, but then you can also add a third frequency and to the bottom electrode. That's a harmonic of the low frequency power you're applying. Based on the phase between that harmonic and the low frequency, you can actually change the skew of the IEDF. Changing that skew then has an effect on the actual process as well, because here you can see that depending on the phase, whether it's at 0 degrees or 100 degrees out, 80 degrees out of phase, you actually get a different etch selectivity between whether it's silicon oxide to silicon nitride. You get an increase in the silicon oxide etching, but then depending on the bias power you put in with the low frequency, you can actually, again, switch it. And it's based on the idea that the skew of the IEDF is changing, and so you have a better selectivity. So understanding the ion energy, or knowing what the ion energy is, has a direct impact on the actual processes that we're trying to complete. Which, if we can understand how to control that ion energy, we have a better understanding of how to design our systems to get the results we want. So when I started, they've done retarding field energy analyzer measurements in the past. They have wafers like these, where it's a actual wafer that you can put on top of the electrode and take multiple or get multiple IEDFs. However, this isn't really conducive. It might not be very resistant to chemical shock, and two, you can't put it in the machine because the machine has robots that'll take the silicon wafers, put them in, run it. So you can't necessarily do that with this wafer. Also, they've taken some of these RFEAs and they have put them in the electrodes in the past, but these were typically one systems. They were a special system designed to just measure the ion energy, run processes, run for commercial systems. In these RFEAs in an electrode for an industrial system. And make sure that it could operate at high voltages, because industrial voltage higher and higher ion energies. And make industrial system as well as a chemistries that these systems or these RFEAs wouldn't see was something I needed to take into account. And then we've found other areas to look at, such as possibly doing a fast neutral measurement with these devices, which is important for aspect ratio in wafers. There's also work looking at as well as ground surfaces, which we'll discuss later towards the end of my talk. So this is the current reactor that I used. It started like this. This is a from Tokyo Electron. It's one of their older systems, but it was something that it was an industrial reactor and designed for industrial purposes. And so I took it from this state into the two states here, which we made this mating piece here that's in the center, which is my actual chamber. It's about a 8-centimeter gap. And then from there, another system from TEL, which was a 200 millimeter SECM system. And the top, we put a 60 megahertz electrode to the top electrode, and to the bottom electrode, we put a 13 megahertz generator. Also in the system, we set it up so it can flow argon, oxygen, and carbon tetrafluoride, or CF4. As oxygen and CF4 are more consistent with actual process gases that you'd see in industry. So I've talked about RFEAs, but it's good to explain how they actually work. So if here on the left you have your plasma, you're going to have electrons and ions that stream from your plasma through your sheath. And in the sheath region, there's a drop in, or there's a potential change. So the ions gain energy, while most of the electrons will get sent back to the plasma. However, some of the very high energy electrons will continue past this first grid, which the first grid is set there to basically mimic whatever potential the RFEA is sitting on top of, because you don't want the RFEA to disturb the sheath or the plasma above it. You want it to be the same so that the ion energy that's hitting one part of the electrode is the same as what's hitting the actual sensor. So then you can be consistent in knowing that the ion energy you're measuring is the same everywhere, or uniform, trying to get uniformity. Yes?
Do you have to have an ion volt, negative, or can you just connect it to grid?
For this first grid, or?
No, for the, all the way last year, you have a battery ion negative.
Yeah. So.
9 volt, you need to put 9 volt, or you can just have it 0 ground?
Well, you could put ground here, but that's going to cause some issues. Because one, the potential on your first grid is going to be negative 1,000 volts. So if you put that as 0, yes, you should be able to measure something from the plasma, because the plasma should be positive, meaning that any ion that comes from the plasma through the detector will reach that collector and be collected. However, because it's a state function, if you're interested in very low energy ions that might have possibly formed in the sheath, by the time it would reach past this third grid, the electric field, because this is at ground and this is some type of positive, is going to actually repel any low energy electron that might have been involved in the sheath. So traditionally, this collector must be referenced to this first grid with some negative potential. The way we did it is our third grid, the scan that we were sending, was connected to that fourth grid, but then I put a 9-volt bias so that there's always an electric field pushing any ion that passes from the third grid towards the collector. So that's a big description about the third grid. The second grid, so as the ions and electrons pass through the first grid, they reach the second grid. The second grid is biased more negative than the first grid to repel any of those electrons that might have made it through the sheath, because we don't want any electrons to enter the RFEA where we're doing earth discrimination, because they could possibly shield the ions from the actual electric fields that are being applied by the third grid. So we remove the electrons, and then, as I stated, ions will pass in between the second and third grids, and we scan that third grid, some negative potential to some positive potential. And depending on what the potential is, it's possible that low energy ions that come in will be rejected back towards the plasma, while high energy electrons pass through, which gives us, at the fourth, an ion energy measurement, or basically an ion current measurement. Based on that current, we know that it is proportional to the integral of the IEDF, so that's how we were able to get our ion energy measurement based on the current voltage curve that we measure with the RFEA. This is a model of the TEL RFEA that I was using, just as a quick background. This is a SolidWorks model made from, or it's a model made in SolidWorks. So this is a computer-generated model. But you can see I've labeled all the different grids: floating, electron rejection, discrimination, then collector. And I refer to it as a collector grid because we added these holes here in the bottom that are chevroned. So you'll collect every ion that passes through pumping. We also have these ports here for differential pumping, and then we have polyamide insulators in between each of the grids to provide electric isolation. And then I also have a couple of lines here, which in upcoming slides you're going to see I ran SolidWorks using EMWorks electric field and across these lines, dashed lines. And then I also mentioned for some future work that we'll discuss is XPDP1 simulations were done between those two grids. So what was the point of developing a high voltage RFEA? There's actually multiple reasons. The first is, again, supplier and industry is requiring higher and higher voltages. For example, high aspect ratio etch is possibly even looking up to 8 kilovolts or 8 keV ions to aspect ratio etches. However, those current probes that you commercially buy can only operate at maybe up to 2 kilovolts. So you can't measure that high energy, or you're going to damage your probe. So to get to those higher energies, we need to make the grid gap distance bigger, because we don't want any dielectric breakdown between the grids with those higher potentials applied between the grids. However, making the grid gap distance bigger brings in some problems. Because making the grid gap distance bigger, you're going to have a higher number of ions and gas particles in between the grids. And depending on Paschen's curve, the pressure could build up enough that you could actually strike a plasma inside the RFEA. So that's why we added those differential pumping ports. If we have a larger grid gap distance, we need to differentially pump it. However, that doesn't necessarily take care of the number of ions that's in there. It's possible that the number of ions builds up so much it actually distorts your curve or your measurement, because the space charge built up by those ions starts rejecting lower energy ions that should have been able to make it to the collector at that point. So we did some simulations looking at electrostatic as well as XPDP1 to figure out, okay, one, how can we optimize the resolution? Because the pumping ports are going to change the electric field inside the grids. So we need to figure out what that's doing and how to optimize it. And then two, we need to figure out, okay, what is the charge doing? So we did electrostatic simulations where we varied parameters like the hole diameter, the grid gap distance, and this fill diameter, which is basically, if you had a circle, the whole grid will actually fill up that whole circle. And the diameter of that circle is what I call the fill diameter. So adjusting those is going to affect our electric field to try, and so we wanted to try to adjust those to make it the most uniform as we can. And then also we used the XPDP1 simulation, the space charge, and figure out what it does to our IV curve and is it possible to compensate for it. So here we have a plot of the electric field using the electrostatic simulation in SolidWorks, looking at how the electric field changes when you go vertically down through the probe. And so this is just the Y component as well. It's the vertical component of the electric field, which is what the ions are mainly going to see as they pass down. And based on this electric field plot here, this is what we expect based on the potential cartoon that we saw earlier on how the RFEAs work, is we have constant electric fields between each of the grids, which is what we want. And then there's sharp transitions as you move from one grid to another. So how does that Y component actually compare to the radial components? Because it's not the only electric field component in the RFEA. If we have a large radial component, that could send the ions away to the walls of the detector, so you wouldn't actually be able to get a measurement. So using a root of the sum of the squares, which is that equation over there on the left, or your right, I was able to normalize the Y component so that you can compare component to the radial component. And as you can see, for a majority of the case, the Y component is the most important, because it basically is, the normalized is equal to 1, meaning it's basically Y over Y. There are a couple of little spots here that dip down, but those are actually due to the sign transitions between the Y electric field, because this is where you're transitioning from one grid to another, and so in that instance, your electric field is changing from negative to positive and vice versa. And so as you go across that 0 point, the radial components quickly are on, I guess, component, but it's only for a small second. So we looked at vertically through the probe, how does it work vertically through the probe? Again, we're using the same simulations, looking at the electric field, the vertical electric field, but just across the horizontal portion, like in the bottom right corner there. And we looked at two regions. We looked at above the polyamide insulator, and we also looked at the hole created in the polyamide insulator just above the grids. And as you can see, we have, in general, a pretty flat field, but at the very edges, you get a sharp transition either up or down, which is interesting because that could affect the actual ion energy as they stream down the probe. You don't want the ions to experience a different electric field at different portions in the probe, because that's going to affect your measurement. So we want to try to basically make this as flat as possible. And since it changes from concave up to concave down, we thought changing those geometric parameters could possibly make it so it's completely uniform. Again, though, we want to make sure that the radial component is negligible. And again, so we used the root of the sum of the squares. And based on the ion region, which is about 0.13 over to just before 0.125, it's pretty flat, which is what we expect and what we'd hoped for. So we know that the radial components aren't really that important in these simulations. So our future work just mainly focuses on this y component. So as I mentioned, we can change the geometry to affect the electric field. And I mentioned that we are looking at the grid gap distance, the fill diameter, and the hole diameter. And in this instance, this is a plot of the electric field at 2 locations above the third grid, at 0.5 millimeter above the third grid on the left side, and at 0.75 millimeter above the third grid on the right side. And then it's plotting the electric field across. For an ideal electric field, in between this or above this grid, it should just be the straight line that you see here at the bottom. I also have these dashed lines here because, as I mentioned, we're changing that fill diameter. So those dashed lines mark the edge of the grid. That's the location where ions would be coming in, is in between those dashed lines for 2 millimeters, for 2.6 millimeters, and then the edge of the plot is for the 3.175 millimeter. As you can see, we get some different at the 2 locations as well as radially across the probe. One, you see this huge discontinuity at 2 millimeters, and there's a slight discontinuity at the 3.75 millimeters. But again, we want just a straight line. So these are showing that the electric field is changing where you are above, or at what portion you're above the, and you also see these drastic changes in the shape on the edges, which again we don't want, and what we saw earlier, and we just want a straight line. And so in this instance, 2.6 is giving the closest, most uniform field above the third grid, as it is straight across the across the 2 portions here, and it's pretty flat across the whole fill diameter. So next, diameter changes that. Again, we're looking at 0.5 millimeter above, and again we see, based on the hole diameter, whether it's at small at 0.0635 millimeters or large at 0.25, discontinuities or variations in the shape across with the electric field across the plot. But again, we want a straight line, and the best straight line that we get, or the closest we get, is with a 0.127 millimeter hole. Lastly, we're looking at the grid gap distance. Now, since we're grid gap distance, it was hard to 2 different. With the grid gap distance change, what the midpoint electric field was like between the grids. One side of the plot here from the center, but then on the right, that's because on the third grid we're actually scanning it. It's not going to sit at a steady voltage, and so we wanted to see what the discrimination voltage is to the electric field above it. For the grid gap distance, you can see that by shrinking that grid gap distance, you actually get a drastic change, especially at the edges of your electric field, which is not what we want. But then with the discrimination potential applied to the third grid, that doesn't necessarily any issue, or it doesn't have an effect on the electric field, no matter what potential you're applying at, which is good. That we could fix. But in general, if we take metric proportions or values that we found and change it, we can change our electric field above the third grid from being something like this, where ions are streaming in and there's quite a drastic difference at the edges, to something like this, where it's pretty consistent across the whole, across the grid. And so that the ions should be experiencing the same electric field and should all be either accelerating or decelerating. And the interesting thing is, this setup that we had to get this optimized version is not unique. You could change the fill diameter, for example, and then change the grid gap distance and the grid hole diameter and get back to this possible uniform field. But by optimizing now, the electric field is not going to adversely affect our actual measurement. So we can move on to look at something that has a more effect on the actual energy resolution, which is the potential in the grid holes. Ideally, when we take an RFEA, we think the potential we apply across the metal grid is going to be the same within the grid holes as well. However, based on the simulation, you can see here in the plot, the case. A drop in potential anywhere from possibly 5 volts to 3 volts in this case, where we're taking the potential at this dashed line here, as this was the point where this difference between what was applied to the grid and what was in the holes was minimal or minimized. And in this instance, we just applied 500 volts across this actual grid. So what does this mean? This basically means, though, that if 500 EV ions are coming in, they should be rejected. However, because the grid hole potential is not 500 EV, those EV ions will still pass through. So we want to figure out how can we get this potential drop here to be as small as possible. So again, we're looking at grid gap distance, grid hole diameter, to figure out how that potential is changing. And in this instance, we took, again, just like that plot you saw earlier, we took the potential drop across each hole, but then we plotted it on top of itself. So that allows you to see the variation between each hole, but then it also allows you to see the variation based on the grid gap distance. And what we find is, yes, there is variation between each hole, but the more consistent or important trend that we see is that with decreasing gap distance, we get an increasing potential difference in the grid holes, meaning that what we're applying to the grid is getting worse in the grid holes because it's not meeting the same potential that we're applying to the grid. So then, because the variation between the holes is not important, we'll just focus on a single hole here, or a couple of holes, but looking at the hole size, what happens when we change the diameter of the grid hole? Well, we find that as we change the diameter of the grid hole, as it gets smaller, the potential that's applied to the grid is able to actually in the grid hole as well. You get a smaller potential difference in the grid holes when they're smaller. And then the last interesting one was to look at the discrimination potential again, because again, we're scanning the discrimination grid, so what does that do to holes? And what we found is that as you increase the potential applied to that discrimination difference increases, which that's a problem because we cannot fix that. We have to apply potential, we have to change, meaning the higher potentials we go, the worse this is going to get. So this is kind of a limiting factor on our energy resolution. But how can we visualize that? So function to figure out how the RFEA going to respond to, for example, a monoenergetic beam of ions. So if we assume that 500 EV are coming in monoenergetic and we apply 500, or we apply somewhere between 499 volts to 511 volts, what we're getting. And if we have just the monoenergetic beam and we have an ideal case, it should just be this step function here. It should just immediately, the current should immediately drop it. However, because we have create these instrument functions by using the ratio, which is described over here on the right. So basically what we can do is we took, for the example, just looking at the grid gap distance, where does 500 volts lie in that potential drop? So if we're scanning between 499 to 511, well, at 500, we know that the physical diameter is that large, and that's where 500 is. However, as you increase the potential maybe up to 505 volts on the top, we know that 500 volts is going to come down here somewhere smaller, which that shrinks the actual diameter there. So that ratio between the top physical diameter and the bottom, or in the ratio or the diameter at 500 volts, you can create a percentage of that's how many ions are going to actually be able to pass through. And that's how we got these instrument functions. And as you can see, as the gap decreases, the width of this instrument function gets larger, meaning that our resolution is getting worse. Because it's not going to be as sharp as a transition with the 500 EV ions, which should measure just be a peak at 500. Instead, with this larger one, it's going to be a peak maybe closer to 504, which means we're now 4 volts off instead of being, for the example, the orange, 2 volts off. So we know that we want to increase the gap distance and decrease the hole size. Decreasing the hole size is good because it gives us better energy resolution. However, it's also going to restrict the actual current coming in. So that one's kind of a trade-off. With the increased gap distance, that's what we wanted anyways, because we want a high voltage RFEA. But as I mentioned, increasing that gap distance could give us problems with space charge buildup. Because what can happen is, as shown in this example from an XPDP1 simulation, is depending on the number of particles in between the second and third grid, you're going to get a potential profile like that up in the top right. And that potential profile, you see a local maximum potential. And it's possible that that local maximum potential could reject low energy ions before, which should have passed through the discriminator and gotten collected. But what you see here in the bottom right is that they're being rejected back towards the electron rejection grid, which is a problem because now we're not getting an accurate IEDF, we're getting something different. So using the XPDP1, we can figure out how does this actually affect our IV curve. But to explain that, we have to figure out, okay, how are we actually going to get our IEDF? And as I mentioned, the current that we measure from the RFEA is related proportionally, meaning we have to differentiate our current. However, especially with a measurement that has noise, problem because any small sharp transition caused by the noise is going to be amplified in the differentiation process. So this is a no-pose problem. But we know that using a least squares regularization method is a good solution method for these ill-posed problems. And basically what we do here for the least squares regularization is we use the equation here where F is our IEDF, K is a system matrix, which you build by making, and in this case we were using, you could use step functions like in the plot above, or you could even make it some type of linear shape where you have the K matrix there where you're going from 1 to 0.5 to 0 as instead of going from 1 to 0. So you basically build your K matrix to model your current. But then you also have this regularization parameter here. You have your conditioning matrix D, which in our case we're just matrix. And then you have, again, your system matrix and your current. And then the alpha regularization parameter be a compromise between how accurate your solution is and smoothing your actual final answer. And you can find a nice balance there using an L-curve optimization. So doing that method, we took multiple IV curves using XPDP1, and we changed the gap distance between the curves. Because if the gap distance was small enough, like a lot of commercial RFEAs that keep their gap distance small enough, they don't have to worry about space charge. And so in the instance here where we have 0.7 millimeter gap, we didn't have any space charge distortion. And that's, you can see the IEDF on the right, that the 7 millimeter gap follows the original distribution used in XPDP1, which is just a typical Maxwellian distribution. But as we increase the gap distance from 0.7 to 1 millimeter, we start to see a difference in the IV curve, which then results in a difference in our actual IEDF. You can see that the rise of our IEDF is earlier with the distorted curves, as well as it chops the top peak off, meaning we're not getting exactly what we should be. So we're getting some type of space charge distortion. But there's a couple of interesting things to note. Is one, we still have our saturation current, which is good, but then there's this point here where all of a sudden the curves all match up again. It follows the same exact trend, which is interesting to note because that means space charge is really only affecting the low energy ions. So if you're taking a measurement, you don't care about low energy ions. Space charge doesn't matter. However, if you want a full spectrum analysis and you want to know about these low energy ions, or you have conditions where it's going to give you low energy ions, space charge could definitely be an issue that you have to take into consideration. So what can we do to try and compensate for that? And the answer that we came up with was, let's go back to the original integral that we looked at before. So the original one is typically, you have your current here, you have your charge, your area, and then you take the integral of your IEDF from basically the energy applied on your discriminator up to infinity. However, because the discriminator is not our peak potential, we're going to change that to what the actual peak potential is based on the space charge. And then doing that, we can look at, okay, let's try to simplify things as much as possible, because we don't know what the IEDF is supposed to look like. We don't know what shape it's supposed to be. So let's try to make a simple shape, which we can make a simple step shape here, IEDF, based on a couple of points from a typical saturation or IV curve. One, we have our saturation current, we have our minimum potential before we get a drop off, and then we have our maximum potential where we're rejecting every ion. So using those, we can basically create this simple step distribution. Using that step distribution, we can then change into a density distribution, which you can see here, where our ion saturation current, our area, our charge, our Emin and Emax, or maximum minimum energies, and then also we have our average energy, or the average velocity of the ions. Now we don't know what that is. However, we can make an assumption. The average velocity of the ions is the velocity found at the point where you get a potential at half your saturation current, which you can see is the equation on the right. Plugging them into Poisson's equations, we can get a model for what that peak potential should be, which is a very nasty equation. So again, just real fast, up here is our original integral relationship. But then if we want to account for space charge distortion, it actually needs to be changed to this, where we're using this model here to get our peak. Well, where did this model come from? It comes from a figure like this, which will hopefully make things easier to understand. So basically, we know that if it were original RFEA with no space charge distortion, the lower limit of the integral should basically follow this red line, where the bottom axis here is on your potential applied to the discriminator, and then your vertical axis is the lower limit value. However, when we introduce ions in between the grids, we know that there's going to be some initial potential, and that's what these lines on the vertical point represent. C equals 0, and as the ion flux, or the number of particles increases, you're going to get an increase in initial potential. But then we also know from what I mentioned earlier and from the IEDFs is there's a point where it also matches on the red line, or the IEDF starts to follow the traditional path again. So the main point is trying to figure out what path is going on between here and here. Because this is the shape of the IEDF is going to change what the shape of this path is between this initial point and the point that it converges again. Now we can actually, based on that Poisson's model, we can get a value for that convergence potential, where again they're related to the ion saturation current and that average velocity, and also the minimum and maximum energies. To try and keep things simple, and where that model that I showed 2 slides ago comes from is, let's just assume it's a straight line. So we have, since we know what our v-intercept could be and what our convergence potential could be, we could then use those values, and where that model comes in is changing the lower limit of the integral is basically truncating your system matrix. Because your system matrix is supposed to model your IV curve. So if we're changing the integral, then we change the system matrix. The nice thing, though, is since we did this in XPDP1, we know what the exact potential is between the grids. We know what it should be, and then we actually have a measured value of what it actually is for space charge distorted portion. So then we can actually, since we know exactly what this point is and exactly what this point is, it was easy to create our 2-point model or our linear model and truncate our system matrix. But then we could also make a more complex one using 4 points that you can also see there. And we could also truncate it exactly based on this known peak potential. So what happens? Does this actually help us recover our IV curve or our IEDF? And what we found is, yes, it does. So on the right, you have using different system matrix. You have the original one, which shows the distorted IEDF, but then you also have your 2-point model, your 4-point model, and then your truncation, or your system matrix that's been truncated based on the exact potential caused by the space charge. And what we find is that even with the 2-point model, which should be the simplest model and the least accurate, we get an increase in accuracy. We get a better peak location, we get a better rise location. It's still not perfect to the XBDP1 distribution, but it's a lot better. And it only gets better as you get a more accurate model of that exact peak space charge potential. So it goes to show that if we can get a good model of that peak potential, then we can account for space charge. Meaning, now the grid gap distance would not necessarily be a problem, and we can use these RFEAs in a much broader set of plasma conditions at higher pressures, higher potentials. So this opens up the diagnostic to a larger area. We just need to keep working on getting a better idea of what that potential is caused by the space charge. So once we have optimized the RFEA, it was time to actually install it in a commercial system. So this is a SolidWorks model of that commercial system on the inside, where most of the pieces here were unaltered. We tried to minimize alteration. The main things that were changed was, one, this electrode was swapped out. What we did is we made the outer dimensions the same as the industrial electrode, so that it would fit right in. But then we opened up a cavity on the inside to actually install our RFEAs. And in some of them, we had it where they were sitting below a drift cone, because the real estate at the top of here is kind of important. There's going to be other things in an industrial system. There's going to be helium cooling channels. There's going to be a different set of cooling channels than the ones we put in this electrode. You're going to have stuff going up to your E-chuck to keep your wafer on your electrode. So there's a lot of different things, and the real estate at the top of the electrode is important. So we needed something that could put the RFEA farther away, and so we have these drift cones. But to make sure that the ion energy we're measuring through the drift cone is the same, we also have a spot where we put one up at the surface, towards the surface of the electrode. And then the other minimum modifications we made is through the center of the chamber, we need to provide different pumping. As I mentioned, if we don't pump it, then the pressure in between the grids can build up too high and we can get light up, whether it's due to Paschen's curve or due to even secondary electron emission, as you'll see in the next couple of slides. And so we have this differential pumping tube that we put through the center, which is typically where the lift pin mechanism to take your silicon wafer off would be. But the tube also allowed us to pull our wires out to take our RFEA measurement. So this is an actual picture of what the electrode would look like, or what the electrode looked like. You can see the backside of the top, which that one I labeled as SM, which is the one it's a millimeter below the top surface of the electrode. And then we have two probes here and here, which sit below drift cones, where one's labeled TM, and that one, first grid, is directly connected to the electrode, so that we know that the potential on that first grid is going to be the same as the potential on the electrode. And then the second one was a floating probe where that first grid just floated, because we wanted to see, okay, what happens if we just float that first grid and we don't electrically connect it. And then here on the right, you can see the lower half of the electrode. You can see the differential pumping hole that we put in, and that's where we pulled our wires out through. And then on top of that, we had a wafer that we wanted to put on, because in a commercial system, the way that this would work is you'd have a single wafer with grid holes. Now that's not what we have here. We actually have a wafer which has a separate silicon grid holes, but this was just done for our concept and feasibility study. In reality, you'd have a single wafer with no extra holes in it that would just have grid holes in the locations where you had RFEAs in your electrode. And as a single wafer, you could put that in your system and say, you know, in between maybe every 100, every 50, or every 100 wafers that you're running, to just make sure your ion energy measurement is the same. So you put it in, the robot would take it, slip it in, set it down, and then you could take an ion energy measurement after every 100, every 200 wafers you run. And so that basically that grid allows access to those differential, or not the differential, but to the drift cones, or to that surface mount probe. And in our case, to keep it on, since we didn't have an E-chuck or anything, to keep it on, we just screwed it onto the top of the electrode. But since we added a drift cone, we need to figure out, okay, pressure is important. We know that pressure is going to, the pressure, it has an effect on our measurement or how the operation of the RFEA. So what change, but we also know the real estate is important at the top of the electrode. So what does changing the shape of our drift cone do from maybe say this to something like this? So using conductor to estimate what the pressure would be inside the drift cone, both at the top and the middle portion. And that's what you get over here in the plot on the right is you have the blue dots, which is the pressure at the top of the drift cone, and you have the red dots, which is the pressure at the middle of the drift cone. I have two other lines plotted on here where one, if you look at the probe and the distance of the probe, we have a specific pressure limit based on the mean free path of the ions in the probe. You don't want the ions to collide with anything in the probe. So that was set to be basically at about a little over, it says it's a little over 8, close to 9 millitorr based on that. However, that's not the only distance. If you have the drift cone, you now have a whole lot of extra distance. So that's what that orange line is it's the, based on the mean free path of the ions through the drift cone and through the probe, that's kind of the operation limit. Now, it's not perfect because for those lines, I was using a single value, but the pressure is changing all the way down this drift cone. But what this plot shows us is the middle of the drift. Any issue there. Depending on the shape of the top, we might have vision. Out because, again, this footprint might be too large for what electrode. You might need to compromise between something like this and something like that up there.
What is the difference between the two angles? You increase the angle of divergence?
Yes.
How much?
So this one, so if you go from 0, that's basically saying that this top side is a millimeter. It is a millimeter in diameter. So 0, basically it's coming straight down.
Oh, right. It's very narrow.
Yeah, and so then going up, we go from 0, and then as that angle increases, it kind of comes out farther and farther to a point where it's about a little over 35 degrees, where that's what this angle is right here for this bottom piece. And so, yeah. So if we take this half angle and make it 35, then it lines up perfectly like that. No problem. So along with the electrode probes, we wanted to also put one in the side of the chamber. So we designed these 2 wall probes, and the purpose for 2 of them you'll see in the next slide. But basically I wanted to give you a picture of what they look like and where they sat. And so basically they sat in the sidewall like this, where this is just a cover to prevent any plasma from going past the probe. We wanted the probe to sit right at the wall, and so we wanted it to act like have a plasma stop. And then in the new one, we changed it so we didn't even need to use this cover. We just made it the complete size. The difference between the two is in this one, you have to pump through the actual RFEA. All the differential pumping is done through this first grid. However, in this one, this is this first grid here. Pumping has to go through this grid, but then it goes around the probe in this other design. But why do we need that other design? Well, as I mentioned, when pressure gets too high between those grids, you can get possible light up. Now, we weren't seeing necessarily light up due to Paschen's curve, because at the pressures I was running at, you need really, really high potential to curve. Interesting effect. One is, depending on the second grid or the plasma electron rejection grid potential applied, whether it was negative 50 volts or negative 100 volts, when this is taken at a ground measurement. So the first grid as at ground, we saw that this hump changes location. there's two interesting things about this hump. One is it's changing location based on that second grid potential. Two, it's also negative. Why do we have this negative hump or this negative drop-off? At a ground measurement, we wouldn't have any of these negative measurements here. What we realized, though, is because it's changing with that second grid potential, it's likely light up caused by secondary electron emission. The aluminum grids that we have, whether it's the first grid or the second grid or the discriminator. So based on this, though, it only occurred at a specific pressure when the pressure in the actual RFEA got high enough. And in our instance, it was about 7 millitorr, or 10 millitorr was the maximum we could run with that other old one. So we changed it to that second design. We saw some other interesting things with our IV curves when taking measurements, whether it was with the wall probes or with those electrode probes. And in this instance, it was this weird linear shape in the negative region that we were a little concerned about. What we found, though, is that linear shape would stop at a specific point, and then it kind of become a more normal IV curve and then continue on. But we also found that that point would move depending on the bias we applied to the collector. So what we realized is when we made these cones, we always assumed the beam would come and just come straight down and we'd collect it and it'd be great. But traditional particle beam reacts is as it travels, it also expands. And the expansion, the ion expansion caused it so that ions would actually travel around the detector. And because the probe was just in the cavity, there was nothing to stop the ions from swinging around the probe and then getting collected by the collector on the sides. So we made a quick cover to cover up the collector and fix this little issue. Another interesting thing we found was these offsets of the IV curve. When at an ideal IV curve, we wouldn't expect any offset. We'd expect it just to go to 0 amps and it'd be done when we're rejecting all the ions. In reality, it's going to be a slight offset based on the resolution of your measurement electronics. In our case, it was about 6 times 10 to the negative 10 amps. However, the offsets you see here are more than that. And so what we realized is the only thing that could be, since we're rejecting all the ions, is it has to be secondary electron emission because it's positive. Well, what could cause that secondary electron emission? Well, we know that there are neutral particles in the plasma, but the only ones that would be anisotropic would be fast neutrals. So it looks like that there was resonant charge exchange occurring, whether it was in the sheath or the drift cone or possibly even in the probe, so that we were developing these fast neutrals which were causing secondary electron emission, which was causing offset. And as we increased the power, the offset got worse. The last interesting thing that we saw in the our IV curves was what happens when we change pressure. Initially, we have a saturation current here, but then all of a sudden, the intensity of our saturation current drops, increasing pressure, which is kind of counterintuitive. You'd expect with an increased pressure an increased plasma density for argon. So what's happening here? It's probably a combination of two things. One is our reactor is actually kind of large, it's at 8 centimeters. And two, especially we have our high frequency attached to our top electrode. So what's likely occurring is there's a localization or a constriction of the plasma towards that top electrode at those higher pressures. To try and confirm that, we took some hairpin measurements to look at the density at the center of the chamber. And in this case, you see something kind of interesting. You see an expected increase. So from 5 millitorr to 10 millitorr, you get an increase in density, which is what you expect. But that's counterintuitive to this drop in ion saturation current. However, the rate at which it increases starts to decrease. But then even at a point where you get to 40 millitorr, all of a sudden the density is dropped. So what I believe is occurring is competing mechanisms with those hairpin measurements is when the density is increasing because of the increase in pressure, but it's also constricting towards that top electrode. However, the hairpin doesn't see that constriction towards the top electrode until you get to a significantly high enough pressure where all of a sudden the density does drop. But that would explain why you get a decrease in the rate of density increase. So we've talked about the IV curves. How is the actual operation of the RFEA working? So in this instance, we have some IEDFs where we compared the wall probe and the surface mount probe, one that's just a millimeter below the surface of the electrode, to a commercial system, a Semian ion or RFEA system done by impedance. And as you can see, the normalized IEDFs, the shapes in general are pretty consistent, and there is some variability in the peak location, but it's possible that's due to plasma non-uniformity or location of the actual RFEAs. But in general, they look pretty good and they look consistent, showing that our RFEAs or the TEL RFEAs were working properly. And you can see that there is some slight difference between the shapes, but we also did this hybrid version where we took the electronics of the Semian probe and connected it to the probe. And when you did that, you get quite a different shape in the IEDF as well, especially over here. Just going to show that it's more likely that it's either the electronics or the post-processing software in the impedance probe that's giving it its smoother shape than what we are getting with our base measurement and our electronics. So then, at single frequency measurements in argon, what do we see between the surface mount probe and between the drift cone probe or the top mount probe? What we see is, in general, we see pretty similar curve or IEDFs. We get what the expected is, with as an increase in energy with increasing power. We also get an increase in intensity with increasing power, which is also what we expect. The difference between the energies is slightly different between the two probes, but again, that might be due to plasma non-uniformity and probe position. The main difference is in the shape, which, as I mentioned, with that drift cone, there's a possibility we could have collisions going on for the ions based on the pressure. And what we see is we see a much wider low energy tail on these top mount IEDFs, which would signify that there's more collisions going on than in this case with the surface mount probe. But in general, it shows that, you know, we can still get an ion energy measurement both at the surface but then also below the cone. Pretty consistent. How does it respond to pressure? Because we were seeing the weird drop in ion saturation current. Well, we see a drop in intensity with increasing pressure between both probes. We also see a decrease in energy, which is what we expect. Higher density, more collisions, you're going to get a decrease in energy. Decrease in intensity is likely due to that localization of the plasma away from the bottom electrode and towards the top electrode. So moving on to dual frequency measurements, interesting characteristics in the IV curves as well. The first was dependent kind of on the actual RF filter we used. We needed an RF filter to take out the RF form that we were sending. We don't want that to either harm our electronics or distort the measurement. But depending on that filter, we either get this negative offset or we can even get a positive offset, whether it's here with the impedance filter or with Allen avionics filters. The only difference that I know of between the two, without actually opening them up and looking at the capacitors and inductors they used, is there's a 200 kilo ohm resistance on the impedance probe that's not on the Allen avionics filters. So that could possibly be a reason why you get this negative offset as opposed to the positive one. However, the Allen avionics filters give us kind of what we were expecting, and those were the ones that we later measurements for this dual frequencies. Another interesting thing that you might note is these curves they do have drop-offs in the negative region, but that's because of the actual reference of the ions. So with the dual frequency measurement, our electrode is biased negative, and that's what the ions are technically, that's the reference that they see. While our RFEA is technically referenced to ground through the computer electronics. So we needed a measurement of the actual potential applied on that electrode so that we could shift the IEDFs based on that potential, and then that would give us the proper ion energy. Because here, if we just take if we did the reconstruction on these IV curves, got the IEDF, we're going to get a peak somewhere here around negative 100, which a negative 100 EV ion doesn't make any sense at all. But if we know that, the actual bias potential is negative 120, then we know that this curve should be shifted to the right by 120 volts, meaning that, that's actually a peak at 20 eV, not negative 100 eV. Another interesting thing that we saw was, especially with the drift cone probes, unlike with the surface mount, which you see in the blue, surface mount one, it was a nice curve and it leveled off. However, the drift cone probes didn't level off. They kept going with this high negative current. We're wondering what could cause that. Well, I believe it's the same thing as we had with the issue with the ions is, yes, ions are streaming down this drift cone, but there's electrons streaming down this drift cone. Now, electrons can stream down. We covered the collector, so it can't be the collector, even though at this point the collector is very positive because it's tied to the discrimination potential. But that cover should stop any electrons from getting to it. However, what I didn't account for was the openings here at the bottom of the base. These screws are recessed, so it was enough that the ion couldn't come and get collected by these screws that are attached to the collector. However, the increased mobility of the electrons due to their lower mass could make it possible that the ions are the electrons are swinging around the probe and then coming and getting collected by these screws. And that's what would be causing this drastic negative current. On these IV curves, how does the actual dual frequency IEDF look like? So with our surface mount and to a degree with our top mount, we have expected saddle shape bimodal peaks. Now I didn't shift the energy of these IEDFs based on the VDC because the VDC, the way we were getting the measurement was a little unique in that we were taking a high voltage probe, attaching it to the first grid of each of the probes, because that first grid was supposed to either be connected to the electrode or floating. If it's getting the proper RF waveform, then you can take the mean of that waveform and that should give you what your bias is. And that's what we did with the surface mount. However, what we found is between which probe we were using, whether it was surface mount, top mount, floating, the average value of that waveform was different depending on which probe. However, because the surface probe was the one closest, I believe that that one was the best accurate measurement of what the bias was, and I later confirmed that with an actual DC measurement from the first grid of the top mount probe, which was electrically connected. But to determine whether the IEDFs were fine, not shifting, it would make sure that the peak location should line up no matter what, if I didn't shift them. And that's what we see with the top mount and the surface, is even though the shape of the surface is quite different, and I believe it's due to the extra electron collection, the peak location is between the top mount and surface mount. The floating probe had more issues. It has this bimodal shape, but it does not look like it had the correct potential buildup on the first grid. So that's the difference. So for future dual frequency measurements, I didn't use the floating probe because it wasn't obtaining the proper DC potential. So then looking at some actual IEDFs from the surface mount probe and the top mount probe, again, we see the traditional bimodal shape, which is what we expect for argon in dual frequencies. And with the dual frequency ones, we have more control. Typically, it's been considered that your high frequency generator controls the density of your plasma, while your low frequency bias controls the energy. Well, if we hold one of those constants, whether it's the density or the potential applied to the bottom electrode, we can determine what's happening with the sheath thickness. And in this case, where we held the high frequency power constant, the density should roughly remain constant, meaning that if we increase the potential applied to the electrode, which is proportional to the potential, or which is representative of the potential drop of the sheath, we know that if that's increasing but the density is remaining constant, then the sheath must be decreasing, which is what we see in the IEDF, because as the sheath thickness decreases, the sheath is oscillating up and down, meaning that depending on how long the ions spend in the sheath is going to depend or cause different shapes. And if it's a small sheath, that means they're going to respond very quickly, pass through the sheath very fast, and basically react to the instantaneous electric fields. So that's why you get this very wide dual peak IEDF. However, if you have a large sheath, you're going to get something which it's a little harder to see here, but you're going to get two peaks that are much closer together. And we'll be able to see it a little better in some later measurements that I'm about to show. But basically, we see that because you have this increasing gap distance between the peaks, we know that the sheath thickness is decreasing like we expect. The top mount probe shows some similar results, but it's interesting that especially at the higher powers, we kind of lose that high energy peak. It's possible that's due to collisions in the drift cone, that it's kind of getting washed out into the continuum or the low energy peak. But in general, you still, especially at the lower powers, you still get that bimodal shape, and the energies are still pretty consistent between the two. It's just the energy here in the top mount probe is slightly lower, which again might be due to collisions. We see a similar trend. As I mentioned, you can hold the high frequency power constant to keep density constant, but then you can also try and keep the VDC constant, or the potential on the bottom electrode. We see a similar trend when we did that as well. So that's why I don't have those shown. Now, we wanted to look at how pressure affects things too, which we see the expected effect with pressure is that, again, we have a decrease in energy. It's more noticeable in the dual energy one. In the high energy peak, we kind of have a decrease in energy. With the surface mount probe, we also see we kind of lose the peaks. I believe it's probably due to collisions. Things are becoming collisional enough that we're kind of losing at 30 millitorr what the actual shape of the IEDF should be. But then the one interesting thing was, so we have a bimodal peak here with the surface probe, or surface mount probe, but with the wall probe we have a single peak, even though this is a dual frequency plasma and it's an RF plasma. And with an RF plasma, your plasma potential is going to be oscillating up and down. And even though the wall probe's at a ground surface, which is constant, because that plasma potential is oscillating up and down, the sheath should be oscillating up and down as well, which should give you a dual energy or a dual peak or a bimodal peak shape for your IEDF. But that's not what we saw, and that's why I mentioned earlier it might be necessary. The sheath models we have at grounded surfaces might not necessarily be accurate, well established to figure, I guess, convince us of why it's a single peak as opposed to a dual peak measurement. So, seeing that we had good dual peak measurements or dual frequency measurements with argon, we wanted to see, okay, how do the single and dual peak measurements work with a process gas? So in this instance, we added CF4, and we wanted to compare it to some previous work. And so in this case, we compared it to some simulation work done by Donko and Petrovich, where they looked at CF4 concentration, where they used a 20 millitorr plasma, a 20 millitorr plasma with 90% argon, 10% CF4, and then they said 60 volts, and they were using 100 megahertz as their main source. Mine wasn't exact. I was using 60 megahertz as opposed to 100 megahertz. I don't know what the voltage was on my top electrode, but the 500 watt case was used because with the same pressure and the same concentrations, the peaks lined up pretty well when normalized. The location is good, the shape is good. So it's a good comparison to show that the IEDFs we're measuring with the process gases are very similar to what we're measuring, or what has previously been done. So then we move on to what the actual probe differences are. Again, we see similar trends, but we wanted to look at how does the concentration of CF4 affect the IEDF. And what we find is that as we move from 0% to 15% CF4, we get a drop in peak intensity and an increase in peak energy in this case. However, in this case, it's a little different. We kind of get an increase in peak intensity, but and an increase in peak energy from 0 to 0.1 or 1%, but then we get that decrease in intensity again. I believe that the surface mount one is due that initial increase, because you're getting a density drop because the CF4 is either de-exciting metastable, so you no longer have metastable ionization of the argon. You also have electron attachment from CF4 or from the fluorine atoms that are in the plasma, so you're losing your electrons or your electron temperatures. So you don't have as much density, so you're going to have a higher energy, which makes sense. But then that also would explain why you have a lower intensity, except with the localization case, where with the localization, the plasma might have come or expanded farther out due to density from pure argon to 0.1 or to 1%. But then as you add more CF4, your density continues to drop, and that overtakes the loss or the decrease in localization. So then we wanted to look at dual frequency measurements as well. And this one's with argon, CF4, and oxygen with a 90%, 5%, and 5% mixture. And again, we were looking at a constant 60 megahertz source power and varied the bias power. And we see a very similar trend again. We see the increasing in peak width. We see some slight differences here in the top mount, but again, peak locations are somewhat similar, and the shape is different due to the electron collection and possible collisions that are occurring. But in general, we see some similar trends as with pure argon, which is a good sign. The interesting thing we saw with the addition of oxygen and CO4 was, especially in the dual frequency case, these multiple peaks. That's kind of what we expect. And as I had mentioned, is depending on that sheet thickness, the ions are going to respond differently. If it's small, they're going to respond instantaneously. If it's large, or they spend a long time in the sheath, they're going to respond to the average changing electric field. Well, that time they spend in the sheath is dependent upon their mass. And with the addition of argon, or with the addition of oxygen and CF4, we now have addition of other ions that have different masses from argon, which would be the cause for these other multiple peaks that we see in the plot on the right. However,
for example, electromagnetic association, and a lot of collision things going on. This is not an easy case.
No. But then what I was about to say too was, with the wall probe, we still have a single peak again though, which is kind of interesting, even though it's at a grounded surface. But again, and we don't have multiple peaks either, which is interesting because, again, we have the mass differences, and as here, you'd expect there to be possibly multiple peaks.
Is it possible to do spectroscopy?
It could be possible with that system. I didn't have a setup to do with that system. The last thing to do was to look at the effects of the CF4 concentration again from the wall probe, and then also kind of the pressure effects. Because again, we've been saying this localization effect. I haven't had great hairpin results to confirm it exactly, but there has been some evidence to show it. And I've got some more here, where again with the CF4, we see this kind of increase from zero in intensity from 0 CF4 to 1%, and then it kind of drops off again. I think it's, again, a localization type effect that's occurring there. But then as you increase the pressure too, with the CF4 concentration, you get the drop in intensity again. So with the hairpin, I tried taking more measurements from the center of the chamber out towards the wall. And what we do see with CF4, argon CF4, is we do have this localization effect, where at 10 millitorr, the density is much higher than going from 20 millitorr and 40 millitorr. Now, we also see a drop towards the wall, which is what we'd expect. But the one interesting thing was with the 40 millitorr is we kind of see the slight increase. I believe that was due to just a hollow cathode effect occurring with the housing of that portion was lighting up. So I was assuming that that portion probably had a higher density than possibly what the center of the plasma might have had. So that's why as we pulled the hairpin out from the center, it's not much. It increased a little bit compared to the previous cases, and so that's why I think it was the hollow cathode effect, because you could see the cathode light up. And
Does that also explain why the density drops on that? Probably sat on one of them too.
yeah, I don't know. I don't believe it was lit up at the 10 millitorr. It might have been lit up at the 10 millitorr case, and I don't think it was necessarily lit up at the 20 millitorr. But yeah, it's possible. So having done this work, it was able to show that, we can take these RFEA measurements in an industrial system, but there's still a lot of future work that could be done. One is design recommendation changes to catch the ion beam expansion. You could increase the grid size. Of course, you can change the grid materials to be more resistant to chemical etching, chemical attack, and different things. And then there's a couple of long-term projects for the fast neutral measurement, possibly using these and that, because you could use the secondary electron emission coefficient material your collector is made out of, take that offset, subtract your resolution, and then doing a reverse analysis saying, okay, this is the current that's being measured as a fast neutral. However, we're actually going to cause a secondary electron. We can get an estimate of what our fast neutral is from that. But then we can look into more of the space charge and sheath effects, which is something I wanted to discuss a little more. Is we do see a little bit of evidence of validation that I've tried to do with some of the wall probe measurements, where I increased the gap size from 1 millimeter to 6 millimeter. You can see that we have this earlier drop off, and we do have this meetup point, which is evidence. However, the problem with this experimental work was this is a normalized IV curve here. The actual currents measured IV curves was drastically different than the currents we measured in the XPDP1 simulations. And it might be due to particle losses at the walls and other effects. And so when we tried using the model and trying to compensate for the space charge, it didn't quite match up the way we were hoping or expected it to. There is some more work that could be done in taking more measurements to validate the space charge effect, and then even trying to make our model more robust to try and estimate what that peak potential is caused by the space charge, so that we can actually compensate for it and get the proper IEDF. The other interesting thing was, as I mentioned with those wall probe measurements, especially in the dual frequency cases, they were all single peaks. Now, most sheath models that are taught or understood are based off of this kind of plot right here, where you have your plasma potential, and then you have some drop off through your pre-sheath, where you reach your sheath and pre-sheath interface, and then you have your wall at the end of your sheath, which is at some negative potential. And typically, at your pre-sheath and sheath interface, that potential is set at 0 volts, which is fine, except when you add a grounded surface, the grounded surface is always at. In that case, you wouldn't have a sheath, you just have your plasma to your pre-sheath to your wall. Okay. However, they say that the drop between your plasma potential through your pre-sheath is typically half of your electron temperature as an estimate. That would give, if you say your electron temperature is somewhere between 3, 5, or even 10 EV, it's going to give you 1.5 to 5 volts. However, as those IEDFs I showed you showed, I was measuring energies from 20 to 80, not 1.5 to 5. So this model here doesn't quite work for an RF sheath at a grounded electrode. It's possible that maybe we just need to change it so that it's fine if we want to reference everything to the pre-sheath sheath interface. That's 0, and then the grounded surface is going to be some type of negative potential. But in general, that's not necessarily how it's considered. And so we can do some more work in analyzing and doing some modeling of the sheath dynamics above a grounded surface for an RF plasma to try and get a better understanding of why those were single peaks as opposed to dual peaks. But in conclusion, I can let you read the rest of this because I've gone quite a bit long. The main point was to, again, try to take an RFEA and put it in an industrial system so that we could take measurements under process type conditions. And I believe that we were able to do that and show that we were able to do dual frequency measurements under process gases and get some accurate IEDFs that were reasonable and showed good energy. And so in the end, I'd like to acknowledge those that have helped me, Dr. Shannon, and as well as Yao, and there's some of their work, Dr. Verbanker, and the help that he gave with XPDP1, Alok, Peter, Joel, Lee, Jing, Barton, Merritt, basically everyone at the Concept and Feasibility Lab at Tokyo Electron in Austin, Texas, as they Electron was also the major support for this work, and I thank them. And there's some references, and if there are any questions, I'd be happy to. Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah.
So you avoid this problem.
Mm-hmm.
I think this can work, yeah.
Yeah, another quick fix we were thinking of was just using some methacrylate and kind of coating it over. So.
So, way we work at the end of the talk, at the end of a PhD defense, is that we open up the floor to the public for questions. This is our first attempt at trying to do this on a live stream, so please do not post your questions to YouTube. We're not checking it right now. Maybe we'll try to do that in the future. But if you do have questions, obviously you can contact Matt or post them, and we can try to answer them later. But as far as the public defense goes, it's now open to questions from the community. It's okay, you can ask questions. I'm not going to come back and nail you on here if you can ask a question. Anything else?
Abdullah came in.
Questions from the, I guess to go ahead and move it forward, the questions from the committee. I mean, there's two sets of questions the committee will ask. We can ask questions with everyone here, and then there'll be a subset of questions we'll probably ask you whenever we ask everyone to go hang out, take the donuts with them.
Mm-hmm.
But is there any questions that the committee would like to ask before we hand all the donuts over to our guests?
I have one question, and you might have covered this, but is it possible to use this thing like a fusion application, super high energy?
You could. The idea was we were trying to design it for higher voltage operation. So, and I did find some papers that have used RFEAs and tokamaks. The designs are quite different. They have to do a lot of more considerations on their material design because, again, you're using such high energies that the plasma hits it, it's just going to kind of sputter away. But they were able to show in those, pass them along to you if you're interested. Energy measurements at the scrape-off layer on the edges of the tokamak plasmas.
Wasn't the electron temperature and gas temperature stuff are high enough?
Yeah, you can melt things.
Anyone? I got a couple I can ask before we. Joe, want to go? Just have the committee. You mentioned when you were talking about your CF4 plasmas that electron attachment makes the electron temperature go down.
Yeah, I realized that I said that. That might be an issue because I was thinking that as an electron, you reduce your electron density, there should be less collisions of electrons, which should increase the temperature.
You're also preferentially killing your low energy electrons.
Yeah, because they're more likely to be attached to the fluorine atoms.
So your
Yeah.
bulk average energy is going to sneak up, and then it'll thermalize. There's a tug of war going on.
Yeah.
But for the most part, you put those things in, you're going to start to.
Yeah, I realized as I said it was probably incorrect, but
Well, I got you.
yeah.
My job's done.
I have a kind of high-level question. Manufacturing. I get the point about you have a kind of a reference wafer that you're using when you're running your events. From an instrumentation point of view, you can measure, nanoamps. You can measure, voltages, fairly well. In terms of your instrumentation and parameters that you're going to be watching or using in this type of thing, what kind of accuracies are you really trying to get at when you're talking about like your ion energies or these parameters? What are you going to measure to kind of dial in your processes? I mean, because traditionally, I think the guy says, 500 watts isn't working, let me try 550.
Uh-huh.
So how are people going to use this information to improve their processes?
Mm-hmm. That's a good question. So on the resolution side, kind of part of that was going over through the design of the RFEA, and that it's kind of constricted by the actual potential drop in those holes. Most systems that I've worked with, whether it was our own or with the Simian probe, typically I think they're looking at maybe 1 EV resolutions, half EV, depending on their incremental steps and things. It kind of depends though, because I incrementally stepped by half an EV, but my resolution might only be 2.5 EV or something based on that system or that instrument curve. So I think they want small, that's best resolution you can get, which based on that is maybe somewhere between 1 to 3 EV, which in general isn't much of an issue because with the dual frequency plasmas you're getting into the 20s, hundreds of EV. I think what they're more concerned about, and Alok might be able to correct me if I'm wrong, but it's more of how to control the shape and kind of the general location of those peaks to affect the processes. And so they don't necessarily need very tight resolution on what the energy is, as long as they have a general idea of what the energy is and where it can be and how that affects your actual process. That's basically what they'd be looking at is, okay, we got this energy based on this configuration. How about what happens to that skew and peak energy when we change it to this configuration, and what does it do to the actual wafer? As far as I understand, that's kind of more of what they're looking at to kind of drive the design process, and understanding what the energy is how can the chamber design affect the energy, which then affects the process.
Right, and I think that makes sense. There's kind of maybe still a question at the kind of the technician kind of level, or the engineer level, how are you matching up that data?
Uh-huh.
Are you just looking to say, well, this curve overlays the other curve, or is it something where I'm starting to drift this direction,
Mm-hmm.
I dial it in?
Yeah, I guess I haven't thought about that far process because, yeah, I guess the way I would expect it is, if they were doing a commercial system like this, they'd publish some kind of baseline data. Is like, if you're running this system under this conditions with this wafer, then you should get this type of ion energy curve. And you might be able to do your own base set if you're running a different plasma chemistry or something and say, okay, this is what I've got, run some stuff and then measure it again. Is it the same? If it is, great. If not, then yeah, I guess that's the way you would be trying to do it, is overlaying it, looking at it and say, okay, well, it's not the same. Based on previous work that I know, if it's something like peak location, can I adjust my bias power to try and fix that? And to see if there's maybe there is some type of drift, or maybe it is because of some type of sputtering coating that's going on in your chamber that's affecting the plasma parameters. And so, yeah, I hadn't thought about that side too far, but yeah, I guess that's the way I would expect it to kind of go on the technician side.
And could you go to slide 49?
Yeah.
So this one you're against theory, and then I think your data, the red and the green.
Yes.
And that kind of strange stuff that's happening with the red curve, so this is kind of, you're measuring, you've got a lot going on, and
Uh-huh.
this complicated plasma system and all that. So the green curve looks so nice, and then the red curve, you've got these, strange, funny
There and
kind of bumps.
yeah. I believe it might be some noise in the measurement that just come through the regularization method, because again, that regularization method is going to accuracy of your actual solution. Because I've done some work too where it's been curves like this, and based on that smoothing parameter I've chosen, it's actually changed it so that the high energy side peak. What?
Careful using the word accuracy.
Okay.
The most accurate one is the one that's your ion energy measure.
Yeah.
But mathematically,
Met-
what you're calling accurate is what?
Trying to think. Now you've put me on the spot and I can't think of anything.
My job, man. These people, they pay me.
So I guess it wouldn't be accuracy. It would be the estimation of your actual solution, because basically you're trying, in this regularization process, you're trying to basically estimate the shape of what it's supposed to look like, as opposed to
What type of analysis? What type of analysis are you, what is regularization taking the place of whenever you set this whole thing up? So what's the if it's not an no-close solution, what type of solution are you usually trying to do?
you're doing a least squares solution, which would be just minimalization of the residual, which
That's what you're calling the most accurate.
yeah.
Okay, so just want to make sure that's not
Yeah.
the most right solution. That's mathematically the most right, but clearly physically is bad.
Yeah.
So just to
Okay. Yeah. Thanks.
Yeah, and so if you looked at like, and this, if you maybe look at your current measurements, maybe you'd have wiggles in your
Yeah.
current measurement that you might have in the red curve, but not in the,
Yeah.
the green curve, and then that's kind of propagating.
Yeah. Yeah. I believe that's kind of what that is.
So you could kind of double check it, and maybe make some type of measure of how smooth that current curve is or something like that.
Yeah. And I don't think I have any of the appendice slides. Because yeah, that's space charge. Well, this is space charge type stuff. Because I had one plot that I ended up taking out, and I think would be a good example where it was funny because, and it was related to this plot actually. I think it's in the thesis, is because this is showing the surface mount and the floating probe, but then the top mount probe, that one looks terrible, like it was oscillating. Every other measurement, not at 500 watts for the top mount probe, at the 400, 300, and so on, looked just fine. And I couldn't see anything in the IV curve that would cause that type of oscillation coming through in the actual solution. And so it's possible that it's maybe something like that, or yeah, it's some just variability and slight variability in the IV curve measurement.
But from a process control point, you just really made me care about the main peak.
Yeah. Yeah.
So while we're over here, you go to slide 46 real quick. I got something you had asked about earlier. I'm curious about. So you mentioned that you talked about the floating probe measure.
Yeah.
And you mentioned that because it's floating, you have basically a voltage divider, so your floating probe measure is giving you a disingenuous estimation of what the DC offset is, right?
Yeah, of what on the electrode is. Yes.
More interesting for me here is why is that would just take your entire distribution function and shift it laterally. But what happens here is your energy distribution has definitely necked down as well.
Mm-hmm.
Can you explain why the distribution function is so much more narrow whenever you're floating your probe?
So to start off with the floating probe, if I remember correctly, the potential I was measuring on that first grid was actually positive. It was around 9 volts, as opposed to what the electrode would be, which is at maybe negative 120 volts. So there's going to be a drastic electric field difference a repelling electric field difference between that first grid and the actual walls, or the drift cone walls of the above that probe, which partly could, that's going to give you a retarding electric field, which could cause that shrinking of the actual IEDF. Shrinking it that much, I'm not necessarily so sure. Again, I know too the shape issue is going to be somewhat caused by electron collection, because that floating probe was also susceptible to electron collection at the screws. But that would be my best guess of why right now, that would be my best difference would be so much, is that you've created a retarding electric field between the first grid, because that's been positively charged, just I believe by Because basically, yeah, again, it wasn't connected to anything except the high voltage probe, which is going to be impedance, so it should just float at whatever potential it's sitting at. And then if the probe's not sitting, again, it's just going to float because the charge has nowhere to go. So it's going to create this retarding field, which should slow the ions as they come down the drift cone, which is.
But if you don't have the fancy mathematical tools at your disposal, how would you take care of the noise in the signal? When you take diffraction, there's a propensity to have huge.
Yeah.
And you don't have.
You don't have the smoothing. Yeah. I would assume, I haven't had too much work with that. I would assume you could try to use some of the electronics in your measurement to kind of reduce the wiggle that goes on. Whether you're trying to increase the actual was the voltage resistor to get current. So depending on the voltage drop I use, I could increase the current value, which might make my signal to noise ratio better, but then it could also just increase the noise. So it's possibly that could work. I don't know if I have a good answer for you now, because I've always had the nice tools. So you could, yeah, a long time ago they haven't, and so I'm sure my grandfather could easily answer that question. Mm-hmm.
Chopper, block, not block, block.
Mm-hmm.
Another question on this slide is what the RF feed penetration in the detector. You have RF and you have DCs.
Yeah. So for these dual frequency measurements, you do want the detector to float at the RF. So you want to make sure you have good, or at least a good potential rise. Now, I'm not necessarily so sure how important that is after the drift cone, because in the drift cone, the idea is, your ions are drifting down. But as I saw with the measurement on the first grid of the top mount probe, that VDC oscillation wasn't as high as the oscillation on the surface mount grid, which was closer to the actual surface. Because the RF is just going to float around the outside of the electrode. So the penetration to the inside of the electrode is going to be more difficult, and that's why I believe the oscillation on the top mount one wasn't as high. However, at that point, as long as the whole detector between the grids are oscillating correctly, it shouldn't necessarily matter. Just as long as the oscillation is the same across the whole detector, because the ions are mainly just going to be retarded by the DC fields. And so as long as the second grid and the first grid are rising at the same rate and same time, then that's perfect. Now, I did calculations, and it was okay coupling between the grids for that purpose. I'm sure it could be made better by putting another maybe capacitor link between the grids.
You do want to float with the cathode.
Yeah, you want.
Not with the top 60.
Yeah, you don't want the 60. And the 60 doesn't penetrate. It does a tiny bit, but it doesn't penetrate very much. For example, with those single frequency measurements, when I grounded that bottom electrode, you would see a little bit of 60 come through on the lines that would affect the potential applied, or basically the way I'd see it was the amplifier I used to set the potential on my second and third grids, it sits at a specific offset when you turn it on, 1.5 volts, 5 volts. However, when you turn the 60 on, you'd see that kind of jump, which that's where I'd see the 60. So I'd put filters on there to take that out from reaching those electronics, but it didn't seem to have an effect on the measurement at all. And so.
Is that you have 8 centimeter gap in this reactor, and if the reactor is like 3 centimeters, you apply 20 kilowatt or something, would that change?
I would assume it would, based on the proximity. It should penetrate more, but then again, depending on what your high frequency is, if it's high enough, your ions won't be able to react to the oscillation anyways. And so because that same oscillation is going to be there in the sheath with the low frequency oscillation as well. And so it shouldn't affect the measurement too much, from what I understand.
For your future work, you discussed that the electronics should integrate for higher voltage operation. What is the limiting factor right now? Why can't you measure higher voltages now?
So what I found was, actually, it comes back to, I don't know if I can get to it. It comes back to the way I referenced my collector and my discriminator together. If I can get back to that really early slide where I kind of had the potential. There it is. So as I had mentioned, we were trying to reduce the amount of secondary electron emission that would occur, which it works for ions when the discrimination grid is close to the ion energy, and the ion will pass through the discriminator. But then you don't want the collector to be so negatively biased, because I don't have a rejection grid. You don't want it to be so negatively biased that the amount of acceleration the ion gets after passing through the discriminator and reaching the collector that it causes secondary electron emission, because that's going to affect your IV curve. So the idea was, okay, let's tie the collector to the third grid. Would just put the 9-volt offset, and so then they should only gain 10 volts as they pass to the collector, which is great. However, so the way the electronics lined up is, and I don't see a marker, that's okay, I had two DMMs, or digital multimeters, that were measuring, one, the voltage output from the amplifier of the discriminator, which in that instance, you have a high voltage line and a low voltage line. The high voltage line can sit up to a kilovolt above ground, while the low voltage line can sit up to 500 volts above ground. For that, it was fine because I was taking the high voltage output of the amplifier, sending it into the high voltage line, and then I was taking the ground signal of that same thing and putting it into the low voltage line, so that was fine. Measurement across the resistor on the fourth grid, because the resistor, there's going to be a potential drop, so the high part of the potential is going into my high voltage line of the DMM, and then the low potential for the potential drop is going into the low voltage. And as I mentioned, that low voltage line can only sit up to 500 volts above computer ground. So if I scan effectively, taking into account what the VDC is, because the VDC changes where I start my scan at and where I finish it at, I could only scan between about -500 to 500 volts, because if I go much above that, the computer's going to throw up an error because that low voltage line is too high above ground. So that's what I wish I could have drawn it, but that's what the main issue was, is basically because the potential drop across that resistor is at a high potential all the time. Possibly. The way I was thinking about it was more of, in the future work, is remove that connection from the third grid, and actually was also considering, put in a plasma, or put in that secondary electron rejection grid. Then you can basically set that collector to whatever you want and not worry about it. In that instance, you don't have to tie it to the third grid, and so that was what my solution would be for quick and easy, is disconnect those. And I could already run some of these probes. Probe where the first grid was separated from the. I had 4 grids there. My first grid, my plasma electron rejection. My second grid is my discriminator. My third grid is now my secondary electron rejection, and then I had my collector. I could run it, and that would have. But with the probe, I should have tried to do it with the floating probe, because I could have done the same thing with the floating probe. Higher potentials with that probe than I was able to polyamide.
As dielectric. Have you, during your modeling, have you considered dielectrics with different permittivity? So I saw you mention in your thesis that peak would be an alternative. Did you model how the electric field would change if you use a different permittivity?
No, I didn't have or think about it at that time when I was doing those, because I was mainly focused on the actual modification of the metal grids. And typically the Vespel or the polyamide, it allows me to run up to 5K with that thickness. So it was definitely good enough to get me to high voltage operation. So I hadn't considered it. But yeah, that would be definitely something you could check later, because you could get a different material with a different permittivity, and you might be able to keep it thinner and still run to those higher potentials.
Have you considered the dielectric loss factor in your simulations?
I am not sure. I'm trying to remember if that actually had an option in there in the actual code or not, and I can't remember. I feel like I saw something, but I can't remember. So I would, to be safe, say I didn't, but I would have to go back and try and figure it out to see.
I think peak might be a very interesting alternative because it has a very low dielectric loss factor, so it might reduce these edge effects with the electric field. But something for future.
Oh yeah, something to consider.
How about the heat rise? Your collector can heat up.
Yes, yes.
Is that a factor?
It can be. In some of the instances, especially most of my powers, I was only running to 600, 700 watts. And that's because of that heating effect, is if I started going to powers higher than that, the collector was having a hard time cooling down, and you'd see basically this resistive current curve that I believe was due to heating. So that is an issue. Typically, though, with cooling the electrode and things, it should keep things cool enough. But yeah, heating can be an issue, and so that might be something you'd have to consider in future work and measurements.
The flow within the cathode, so it will be cooled down.
Yeah, yeah,
You don't have that problem in real world.
yeah, yeah.
Do you think you'd have seen that second peak on the floating probe if you were able to bias it higher? If it was almost kind of maybe shifted off. Biasing it. It would have been just after that you would have seen a second peak if it were to be there, if it was just those other peaks, or if those other two curves shifted off to the side. Does that make sense?
Not quite. So yeah, I'm understanding you correctly. You're thinking that the two peaks that I saw were technically just a single peak that,
From the left side,
yeah.
Just the entire thing shifted off to the side, and because you had to cut it off at whatever bias you did, it just cut off that second peak that would have showed up.
It's a possibility it could have. I would be a little skeptical of that based on just the way the other curves responded and the way the IV curve shape looked, because by the time it would have had to be drastically different, and it would have been really on the negative end of that curve, because the floating probe was susceptible to that electron collection, and so it would have been really in the negative side too, which but that was definitely something I would be able to figure out if I had covered those screws and gotten rid of that electron collection, because I would have been able to see if it just flattened out. Because if it just flattened out, I would say no. If it continued to kind of drop, I would have looked for it and.
Point where it cut off, it was increasing. Page first, slide 46.
Yeah. So you mean that portion right there? Yeah. It's increasing, but so those peaks came from these IV curves. And again, that increase is probably due to increased electron collection, because just as this one's going down, this might continue to change slope, which is going to cause that increase. It might level off eventually, kind of like the top mount one did, and just stay a same slope. But yeah, based on the initial shape here is, to me, it seemed that this was IV curve. I didn't get any other IV. And then it leveled off a lot and then dropped again really heavily. So that's why I'm kind of skeptical of the idea that if I kept going, it would. But it's something to consider. And like I said, if we had collected or covered those screws and didn't have this electron collection, it would have been a quick and easy thing to figure out, because this would have really leveled off flat if it was done.
Any more questions? Okay, at this time, if you're not sitting in the first two rows, I'm going to invite you to take the donuts outside, have a snack, have some cider, hang out for a bit. Committee members, if